So what are the objectives of this lecture? Well, we'll start by bringing in the data from the coin toss. Then we'll talk a little bit about distributions of processes and populations and how averages distribute themselves. Because distributions of average is something that is frequently used in social science analysis. Then we'll talk a little bit about hypothesis testing, and we'll do a specific test of the hypothesis that the coins are fair. That is, that we expect to get 50 heads out of 100 flips. Then we'll talk a little bit about comparing the means of two samples, and we'll do some hypothesis testing on two different samples. The sample of individuals who started on heads versus the individual who started on tails, and then we'll also compare the means of the men and the women to see if gender produces a difference in the results, and presumably there won't be any difference. And then finally we'll do a little bit of discussion. So the protocol for this session is as follows. The first thing we'll do is we'll inspect some of the results from the coin toss experiment. Then we will discuss the distribution of the coin tossed and other types of different distribution. And we'll talk about these in a fairly limited way. In the actual workshop, we had a somewhat longer discussion, but it's hard for me to discuss with myself. Then we'll download the tool JASP. I won't actually do this in the video, but we did this in the workshop, and the video will contain the address you can download it from. And then finally, we'll do some hypothesis testing using JASP and the coin toss data. So the basic idea of a distribution is that whenever you have a process or population that you sample, you're going to get a certain number of observations at each value. And if we have continuous values, it's a little more complicated, but if we have discrete values like a coin toss, which is to say values that are 49, 50, 60, there's no 40.73 when you're flipping a coin 100 times, then we get something that is essentially a frequency distribution. And the frequency distribution I have drawn here looks a little bit like the well-known distribution, the bell curve. And we'll talk a little bit more about bell curves, also known as normal distributions or Gaussian distributions, shortly. But the idea is every process has a distribution of values, but not all processes produce distributions of the same shape. And one big mistake that you can make is to assume that a distribution is going to produce a nice bell curve when in fact it doesn't necessarily produce such a curve. So in the workshop, we actually had a discussion of how different things might be distributed. It's not very good to do a discussion in a lecture format, so I'll just kind of review some of the things that we talked about. And the point is that not all variables are distributed in the same way. So consider the single coin flip. The single coin flip can have two possible values, heads or tails. And so basically you're going to have a frequency diagram of heads or tails if you do a whole bunch of coin flips. And that is sometimes known as a binomial distribution. There are actually lots and lots of binomial distributions possible because your options don't have to have the same probabilities. You can have multiple outcomes and so forth. And binomial distributions are a type of distribution where when we teach a probability course, we spend a lot of time giving you formulas to compute the probabilities of different occurrences. They have lots of factorials in them and that sort of thing. Because it's one of the few types of probability that we can actually compute reasonably well. And we could do the same thing with a die. Whereas a coin flip has two possibilities, a die has 6 possibilities. And so if we were to flip a die and create a frequency diagram, we get values 1 through 6. each equal. Now, if you start adding dice, 2, 3, 4, 5, then it becomes more complicated. If you've worked with dice, for example, you'll know that the combination 7 is more common than any other combination when you're flipping 2 die. And so, as you start to flip 10 die or 100 die, all of a sudden you start to get different distributions. But the point is, those things can all be computed because we know the individual probabilities. In most management situations, we don't know those probabilities. We can't make estimates that way, and that's the reason we don't exert a lot of time into understanding all the different combinatorial formulas that are out there. Now, another type of distribution might be the distribution of how many flips you need until 8 heads in a row are achieved. And, don't hold me to this, but I think that might be an example of a Poisson distribution, a distribution that basically says how long you have to wait before multiple occurrences. It also is going to look probably a little bit like an exponential distribution. And a good example of an exponential distribution is the time that we expect to wait before a light bulb fails. And the way we compute that is we assume that there's a given probability of failure at any given time, and it doesn't change no matter how long the bulb has been going. So if you manage to say a light bulb has an expected life of 100 hours, if the light bulb has been going for 100 hours, the expected life is still 100 hours from that point on. But if the expected life were 100 hours, or we had a 50% chance of it failing within 100 hours, then half your bulbs would be out at the 100-hour point. 3/4 would be out at the 200-hour point. 7/8 would be out at the 300-hour point. 15/16 would be out at the 400-hour point. But at that point, those 1 in 16 bulbs that were left would still have an expected lifetime of 100 hours. So that's an exponential distribution. Once again, I'm talking about these things quickly, and I don't expect you to really understand them because, for the most part, we don't deal with these types of distributions when we're doing management research. And if we do, there are plenty of books on them. What I do want to emphasize is that these are not bell curves. These don't look like bell curves. Now, what does look like a bell curve, it turns out, is the chart of individual heights across a population. And a lot of social science variables actually look like a bell curve through most of their distribution. The bell curve, also known as the normal or the Gaussian distribution. The bell curve is also very important for another reason, which we'll talk about in the next slide, called the central limit theorem. Then there's the distribution of, say, wealth across a population. Now, this is definitely not a bell curve or normal distribution. In fact, I was reading in the Wall Street Journal recently, in the not-too-distant future, half the world's wealth will be concentrated in 1% of its population. That's a distribution that is consistent with something called a power law. And a lot of variables, such as wealth, populations of cities, distribute themselves according to this kind of power law. And if you mistake a power law for a normal distribution, you're likely to get some very serious errors, because when you have these big concentrations, you can't really ignore them. And the example that I give is Bill Gates, who is, if you look at the Harvard class of 76 and the Harvard class of 77, the Harvard class of 77 has a net worth on average of $3 million more per student than the class of 76. Why? Because the class of 77 had Bill Gates, and you take his $40 or $50 billion and divide it by the number of students, and suddenly you have a big difference in the averages. Now, for something like that, the median might be a better measure, but again, if you're thinking about who you want to get donations from, you might actually be very interested in those outliers. So I keep referring to this normal distribution, Gaussian distribution, bell curve. As I emphasize, they're all the same thing. And there are reasons for this. The first reason is that a lot of populations actually have variables that follow a normal distribution just naturally. Things like distributions of heights, distributions of intelligence, and so forth, tend to have a lot of their data or observations falling within this bell curve. They often also have outliers that are more than what the bell curve would predict, and I'll explain this shortly. But the bell curve is very, very easy to describe. It's got a mean and a mode that are the same, which is to say you're going to get the most observations around the mean. If you move one standard deviation away from the mean, then you have about 2/3 of your observations sitting there. If you move 2 standard deviations away from the mean, you have about 95% of your observations are going to be contained in that range. If you have 3 standard deviations away from the mean, about 99% of your observations are going to fall in there. And if you move much further away from the mean, there are virtually no observations. The bell curve falls off very, very fast at its outer edges. As I say, in real world, sometimes you will have what's called a long tail, which is to say you'll have more observations, 4 or 5 standard deviations away from the bell curve mean than you might otherwise expect. And that can cause problems in some circumstances where those observations are very significant. So you can't always guarantee a bell curve. Now, one of the reasons that the bell curve is so prominently used in statistics, aside from the fact that a lot of social science variables tend to naturally group like a bell curve, is something called the central limit theorem. And what the central limit theorem says is that whatever distribution your data comes from, whether we're talking about binomial distributions, Poisson distributions, exponential distributions, all these distributions that I haven't talked about, if you take the average value with a lot of observations, the average is going to tend to be distributed according to a bell curve, no matter what the source distribution is. So in a certain sense, when we did a coin flip 100 times, we're taking the average value of a coin flip for 100 observations. So instead of saying 50, the average is something like 0.5. Well, what it's saying is that those averages are likely to be grouped according to a normal distribution. And since in the social sciences a lot of time we're asking if the averages of 2 different samples are the same, we can often use that normal distribution assumption as a good way of determining whether or not these averages are different from a statistical standpoint or whether they're just different as a result of randomness. So why do we care about this central limit theorem? Well, there are a number of reasons. Of particular importance, very often in the social sciences, we find ourselves comparing sample averages. And because of the central limit theorem, when we're comparing those averages, assuming that the average distribute themselves normally is not such a bad assumption. It also means that the standard deviation, or the variance, is a very important tool in determining whether 2 averages could come from the same population. And so you'll hear a lot of techniques called like analysis of variance, multiple analysis of variance, ANOVA, MANOVA, and so forth, that take advantage of this fact that we expect the distribution of the averages to be normal. When we can assume normality, we can ask a lot of interesting questions, such as, do 2 samples appear to come from the same distribution? What is the likely range that we're going to see of variables if we sample from this population? And what is the likelihood that the patterns that we're observing in our data are random as opposed to being actually indicative of a particular difference. And what we're going to do shortly is use the statistical tool, JASP, to actually do some analysis on the coin toss data that was gathered during the workshop. So let's talk a little bit about the type of questions that we could answer before we actually go into the analysis of data. And here are the results of some simulated data. I didn't bother putting the classroom data in here because frankly the classroom data came so close to the mean that you'd probably answer the question without thinking about it. But in this simulated data that I used with Excel, we had an average of 25 tosses producing an average value of 47.9 heads with a standard deviation of 5.44. And so you can see this chart has a significant standard deviation. And the question is, is a fair coin likely to yield these results? And this is exactly the type of problem that we would try to attack using techniques like analysis of variance or the very simple t-test. And that's what we'll do now using the software package JASP. In the previous example, what we were trying to do is to compare a distribution to a hypothetical mean. In this case, we expected a mean of 50. But another way we can use this tool of analysis of variance is to ask if the averages of two distinct populations were likely to come from the same underlying process or population. And you can never know this for certain. I mean, it's possible if you flip a coin long enough, you can get 100 heads in a row in 100 flips, but that would take a very long time, approaching the number of atoms in the world and stuff like that. But at any rate, the point is we're trying to figure out the likelihood. So in one case, we might have two distributions that look like this, and so we get two samples, and the question is, could those means have come from the same distribution, maybe a distribution somewhere in the middle? And in this case, there's quite a bit of overlap in there. We might say, yeah, that seems likely. Well, statistics allows us to sort of quantify that likelihood. On the other hand, we might have two samples looking like this. Now, in this particular case, it seems a lot less likely that those two means would have come from the same distribution because the overlap between them is very low. And this is the type of thing that we can do by making the assumption that averages are normal and that they have and that we can compute the standard deviation based upon our sample. And all of that stuff happens behind the surface when you're using a statistical tool. So you don't have to worry about the actual computation, but you do need to have at least a sense of what the tests are called and how you apply them. So that's what we're going to come up with shortly. So before we start working with the actual data, why don't we just sort of review what we're trying to do in terms of our research objectives experimentally. And there are typical research objectives that we might have. One might be to determine if a particular sample actually comes from a distribution with a particular mean and standard deviation. And the example of that is the coin toss. Is our coin fair? But there might be other circumstances as well. For example, we know that roughly 50% of the population is male and 50% is female. It's actually slightly skewed towards female, but the numbers are relatively small. But so if we did a sample of, say, 40 people, and of those 40, 10 were male and 30 were female, we would ask, well, is it likely that we were sampling from a population of equal numbers of male and female. And so there we have some anchor, whether it be 50-50 or something that we expect. If we were rolling a dice, we might ask, does the numbers that came up from the dice, are they consistent with a fair die, or are they consistent with a loaded die? But another time, what we may be doing, and this was the second slide that we just covered, is we may be looking at two distributions and seeing the likelihood they came from, or two samples, I should say, and see the likelihood that they seem to come from the same distribution. So in the case of our coin tosses, we might want to find out whether people who started with heads have the same average as people who started with tails, or do men flipping coins have the same heads and tails average as women flipping coins? And one of the things that we use for this is this p-value that I talked about in the previous lecture. And the p-value is just a kind of an estimate of how likely it is that a particular sample came from a particular, met a particular criteria, such as the means of two samples were the same, or a particular sample has a specific mean. And what the p-value does is said, how likely is that compared with the likelihood that they have different means? So that what it's basically doing is it's saying, how often would we expect random distributions with a particular mean to produce values similar to what we have? So it's really a test against randomness. As a standard in research, we look for low p-values as a way of saying, no, we think that the sample we have is different from this base case, which might be that two samples have the same mean, or it might be that the mean is a particular value. And the 0.05 is somewhat arbitrary. It was developed by an individual named, it emerged out of a lot of different places in the 1900s. But it's become kind of the standard of sciences. So when you see people using p-values of 0.1 instead of 0.05, so it's like a 1 in 10 chance it could be random, that's usually a sign that their data didn't come out quite as well as they hoped. If you start seeing p-values of 0.01 or 0.001, what they're saying is, really, this appears to be a very strong effect. It's very unlikely that it's random. All of this leads into the notion of hypothesis testing, and a lot of academic research is built around the notion of testing whether a particular proposition, which we'll call a hypothesis, is true or false. And statistics play a big part of this in terms of empirical research. So the way we typically frame this is the null hypothesis is the hypothesis that whatever we're looking at has no effect. So the null hypothesis in the case of a coin flip would be that the odds of getting heads is 0.5. The null hypothesis in our experiment might be that the odds of starting with heads or tails are basically the same. The null hypothesis on gender is that gender does not make a difference in terms of the percentage of heads and tails you would get. So the null hypothesis is basically saying our research has not found any effect. And so most of the time what we're interested in doing in our research is identifying an effect. And by the way we do this is by rejecting the null hypothesis. And this usually occurs when we have a p-value of less than 0.05. And this is why p-values crop up all the time in research. Now, whether they should or not is a question of some controversy, and there's some research in the social sciences which has gotten very frustrated with these p-values and would rather use other things like confidence intervals, which is basically a range. But most research is going to publish p-values, and when you see a p-value less than 0.05, they're going to say that's significant. That is a basis for rejecting the null hypothesis based upon the sample that we had. And a lot of our statistical, a lot of our research design is built around coming up with clever ways of gathering data so that the test is really a rigorous test of the particular hypothesis we're looking at and is not interfered with by lots of other types of data. For example, if you were trying to make an estimate as to how far people or how long it took people to get to the office, you might decide you want to separate out those people who walk from those people who drive because they might have a fundamentally different dynamic. Now, in practice, hypothesis testing might be a little bit limiting because a hypothesis test, for example, just tells you that the two means are not equal. It doesn't tell you which mean is higher, and more important, it may not identify an effect that justifies the cost. As I suggested, if we flipped a coin 10 million times and had multiple replications of this, there's probably a pretty good chance that it wouldn't exactly be 50-50 heads and tails. But it would be close enough so that it would not be worth the effort to try to adjust for it when you have a normal coin flip, at the beginning of a football game or something like that. So under those circumstances, you wouldn't want to make the investment to flip it 10 million times when you know it's really close to 50-50. On the other hand, if you think it is a big effect, if it's 25-75 or something like that, under those circumstances, it might invest in, if you were a football coach, you might invest in that type of research if you thought that the coin flip was really biased. Another thing is that research built around hypothesis testing may not necessarily generalize. It might be interesting from a research standpoint, but if your business is operating in a different context, you may well find that a hypothesis that gets rejected in one condition, has to be accepted in another condition. And this is one of the advantages of basically doing your own research, is that at least when you're researching your own organization or your own situation, you don't have to worry about whether or not it's going to generalize to you because, in fact, you are, in fact, researching your own organization. So some of the techniques that are potentially powerful for determining if there are effects there are even more powerful if you're doing it on your own business and you don't have to worry about whether the context in which it was done was very different from your context. So what I'm going to do now is a few analyses using the open source statistics package JASP, which is just a very nice package for doing some basic analyses. And this includes analysis of variance. It includes t-tests, which are the basic tests that you can use to compare two means. And it also is very nice for multiple regression analysis. And I'm not going to bother downloading it in this video. I'll use the copy I already have, but we have the address here, or you can just Google JASP and find out where to download it. And a very quick download. It probably takes a total of 2 minutes to download and install it. And it's really a very easy to use package. So what I'm going to do now is I'm going to move away from the slide deck and bring up JASP. It's located on my computer. And the first thing that I need to do is load in a file, and I'm going to load in my Survey 2 coin toss results revised, which is the original results with an outlier or two removed. And so if we take a look at the data, what we see here is how many heads did you get out of 100 tosses, how many times did you get 8 heads in a row, how many times 8 heads or 8 tails in a row, maximum number of heads you had in a row, maximum number of tails you had in a row, what's your gender, what was your assigned flip position. And JSP loads CSV files, comma-separated variables, which is exactly the way that your data comes when downloaded from Google Forms. Now, Google Forms has a number of challenges. Very often you'll have to massage the data, bring it into a statistics package, but in the case of this particular experiment, we didn't have to. So what we're now going to do is we're now going to run a series of tests using JSP. And the type of test you use to compare means, or to compare two means or one mean, is a t-test. This comes from Student's T distribution. Student was actually a brewer at Guinness, and his last name was Gossett, and he developed this test, and this test turns out to be really nice for things like multiple regression, because there are a number of variables that distribute according to a t-test. As you get a large number of variables, the t-value is very similar to the number of standard deviations away from the mean in a normal distribution. I think once you get over about 30 observations, the t-value pretty much becomes similar to the number of standard deviations away from the norm. So a t-value of 2 is going to produce a p-value of about 0.05 because 2 standard deviations away from the normal distribution only holds about 5% of the values. So the first test we're going to do is a test to see if the mean is 50. This would be a one sample t-test, and the variable we're going to be looking at is how many heads. So we have how many heads over here. And JSP constantly gives you values here, and so it basically gives us a t-value of 49.36 and a p-value of 0.001. Well, the reason for this is I haven't actually told it what mean to compare it to. So what we're saying is the odds that the mean is actually 0 is totally inconsequential. 49.36 is like 49 standard deviations away from the mean. That really is unlikely to happen. So as a consequence, let's set a test value of 50, which is what we would expect out of 100 flips, that you'd have 50 heads. So when I put 50 there instead, now we get a t-value of 0.489. We have 25 degrees of freedom. Degrees of freedom is basically the number of observations minus the number of variable number of statistics that you're pulling out of it, something like that. So in this case, we're looking at one variable, so there are probably 26 observations. The p-value is 0.629. Now remember, we're looking for small p-values if we're going to reject the notion that it was 50. And in this case, the p-value is very high, which means that this distribution very easily could have come out of a distribution with a mean of 50. And if we actually take a look at the descriptive statistics, which gives us things like means, if we look at how many heads you have, what we see is that the actual value was 50.5 for the mean. And so that gives us a pretty good sense of the fact that it's unlikely that there's a big difference between the percentage of heads and 50. Okay, so this was testing a single sample. Now, suppose we want to test the proposition that whether you start in heads or tails does not make a difference. So the null hypothesis is that the mean for flips starting on heads is going to be the same as the mean for flips starting on tails. The way we do this is with a independent samples t-test. We're not going to do a paired samples here, but a paired samples is normally a before and after, where you're dealing with the same observation in both cases. For example, you start out with a group of people, ask them how thirsty they are, you give half of them a drink, and then you have them report how thirsty they are, and likely the ones who were given the drink are likely to be less thirsty than the ones who were not given the drink, that type of thing. But in this case, the before and after are the same observation. Well, in our case, it's not the same observation, it's different observations, so we have independent samples. Again, the dependent variable, and the dependent variable is the one that you're trying to predict, is likely to be how many heads did you have. And the grouping variable is what we're going to use to create the different means that we want to compare. In this case is what was your assigned value, heads or tails. So now we're going to do a t-test here, and I think that what I need to do here is I'm going to expand the window a little bit. I'm just going to bring this thing over. You already see how I created it, and I'm going to just give us a little more room so we can see this. So how many heads did we get out of? The t-value is very, very small. Degrees of freedom are 24 because now we got 2 samples. The p-value is 0.971, which is basically saying, wow, these 2 means look almost exactly the same. If they look different, you'd have a p-value of less than 0.05. Okay, so what that tells us is we cannot reject the null hypothesis that the 2 means are the same for people starting off heads, people starting off tails, and so as a consequence, under these circumstances, we would say it seems like it doesn't make a difference. Now, in the case of heads and tails, the way I set up the experiment, we have roughly the same number of people tossing with heads and tails. Now, we did not have the same balance in gender. We had a significantly more men than women in the experiment, but the statistics package does the same, can do the analysis either way. It just has to make some more assumptions regarding things like, are the variances of the 2 samples the same, and so forth. So in this case, what we see is a t-value of 1.147. That's a little higher. If the t-value is 2 or more, chances are the p-value is going to start approaching 0.01, depending upon the, or 0.05, depending upon the sample size. In this case, the sample size isn't very large, so you even need larger t-statistics. Basically, as I say, the t-statistic is like the number of standard deviations away from the mean. The only big difference here is that the t-statistic adjusts for small sample sizes. So at any rate, we see 1.147 here, and the big thing is the p-value. It is 0.26. Basically 0.25 would be 1 in 4. That's still not far enough from random for us to throw it away, so we're going to have to also conclude that the men and women flipping the coins are likely to have the same 50-50 chance. And, that's good, because I would be really concerned if we saw a big difference there. But this is how you can use the JASP package to do some very simple hypothesis testing. So we've now seen how we can do some very simple hypothesis testing, and we've seen how the tool JASP gives us the ability to do this type of thing easily. JASP is not the only tool. It is much less sophisticated than other tools that are available, such as SAS, SPSS, or R, but it is very easy to use, and it's good enough for our purposes. Now what we want to do is we want to think a little bit further, and we want to talk about some more advanced analyses, and specifically we'll talk about the notion of correlation, how variables change in conjunction with each other. We'll talk about interaction, which is somewhat similar to correlation, but a little different. This is the way variables affect each other and affect your dependent variables. And in high interaction, you're more interested in combinations than in individual variables, and we'll go over that in some detail. Then we'll talk about some of our linear models. As I mentioned, hypothesis testing is not necessarily all that useful for managers, because managers really want to use the data that they're analyzing as opposed just to make statements about truth or falsity. And so sometimes what you really want is a model that will allow you to make predictions of value. So the second half of this workshop focused a lot on things like multiple regression, which is an example of a tool that you can use to actually build models to help you predict and understand behaviors. And it can also be used for hypothesis testing. Then we're going to talk a little bit about covariates. Sometimes you're trying to do a test, but at the same time there are factors that affect the test, and what you're trying to do is remove the influence of those factors. so that you can conduct the test purely. And we'll do this as an example using a survey we've done of height and ideal weight, because that's an example of something where gender actually could have a big influence on what the relationship is. We will then talk about multiple dependent variables. There are techniques such as MANOVA, multiple analysis of variance, that can be used when you've got multiple variables. There are also techniques such as analysis of variance, which can be good if you're trying to break up your sample into multiple different groups as opposed to doing a simple pairwise group like we did in the t-test. And then we'll talk a little bit more about this notion of modeling versus testing that I just talked about.